All right. Welcome. My name is Roland Barcia. I'm the Worldwide Director for our Specialist Technology team. I have the honor to be presenting with much smarter people, Christina and Victor. They will introduce themselves when they start speaking for the interest of time. So let's get going because we have a lot of material to get through. This is a 400-level session, so we want to go deep very fast. I'm going to kick it off and kind of set some context before I hand it off to Christina. And we're going to talk a little bit about data to start. Obviously, in a conference where we're talking a lot about generative AI, LLMs, Bedrock, et cetera, data has become probably one of the key commodities that we have. And there's lots of it, lots of different data formats, lots of different users or personas of data. It's no longer just analysts anymore. It's developers use data, end users use data, internal folks use data, and people need to make decisions fast and quickly. And so when we talk about data, we want to think about personas because we're at AWS, we're customer obsessed. And we got to think about data from a perspective of who uses it. And so we're going to get a little bit deeper into things like data processing with Spark as an example. But we want to think about things like your external users. So you have data that you expose as part of your business to your users. Oftentimes you have historical data, batch data, things that people look at monthly, weekly, that have a known pattern. And more we have a need to make decisions real time with data. This is probably where we see a lot of generative AI use, right? Where people are using prompt engineering and things to do ad hoc queries, ad hoc answers to questions and things like that. Internally, we have personas that want to make use of data to make decisions about anything and everything from how do I run a system more efficiently, how do I scale it better, what are some security audits that I'm seeing, and observability tools kind of help out there. And then we have to process lots and lots of data, right? So we're going to get into things like Spark and its cluster technology and things like Hadoop in the past, and then emerging technologies like Flink that have kind of brought together, how do I process streaming data as well as batch data together to make these decisions. And so let's talk a little bit about platform engineering. A lot of our customers have standardized on Kubernetes. They use EKS, Elastic Kubernetes Service. Some great announcements this week and other sessions in the track, like auto mode and things like that. But oftentimes, when you are a startup, maybe you have just a development team and you do platform engineering as part of that development team. But over time, as you grow, the emergence of platform engineering has come about with Kubernetes. And a lot of those concerns really focused in the first generation around web applications, microservices, event-driven architectures, and this emergence, I always call it a little bit of a collision between personas and goals, right? Where developers wanted freedom, they want to use their favorite open source tools, their technologies, they want autonomy. I want to build a new app, I want to deploy it, I want to get it out quickly. And then you have platform teams that are worried about things like the security of your systems, scalability, cost, performance. And so the first generation of these platform teams are really thinking about web applications, microservices, transactional systems. And platform engineering has really emerged as a way to kind of meet in the middle between providing this autonomy and still automating things like standards in a developer-like way. There's lots of talks on overall platform engineering. I have one on Thursday in the serverless track from the developer persona point of view, the users of the platform. And so you can come to that session when I get into it. But when we're talking about platform engineering, one of the things that customers often struggle is where is that line between the developers and the people that use the platform and the platform team? Do I vend out clusters? Do I vend out code as a service? Do I make it easy for developers to just check in code? And so these are the first generation problems. It's all been solved, right? But probably not. There's still probably lots of debate here on where the line stands, and that's because of the workloads. And so we get now into the age of data and lots of data, and data scientists and engineers have started building things with notebooks, using SQL, data processing. They're building stateful applications. They're building applications with streaming and events, workflows. They're using notebooks with Python or R to build applications, and notebooks that are doing generative AI or ML or any type of data processing. They're building data lakes and data meshes and applications that sit in front of them to kind of federate the data. And the platform team all of a sudden has to worry about things like, what's the optimal storage to use? Do I give them GPUs? We have cool Inferentia 2 and Trainium 2 announced this morning that we kind of heard about as well, right? And we have new types of DevOps, MLOps, data pipelines, the life cycle of an LLM, the life cycle of my data. So these are now new concerns in this next generation. And so I'm not going to go into all of these in exhaust, but there's a lot of goals for platform engineering and data workloads, right? So how do I get the right resources? Developers want to get the right type of machine type, the right type of GPUs, the right storage type for their workloads, for their notebook, for their data processing. They want the right security, the right isolation. They don't want a data job running over here to interfere with a transactional system over there. And I want to do it at the best price point possible. And of course, just like developers, data scientists, data engineers are very opinionated about their favorite, PyTorch framework, TensorFlow, all the different types of frameworks out there for doing data applications. And so how do I support that autonomy with this new generation of applications that are very data intensive? Lots of different challenges with stateful workloads, right? We're talking about things like, how do I use thousands of nodes, or even the opposite problem, really large images that take a while to start up, to warm up the data. And some of the things in Kubernetes were really optimized in the first generation to spin up compute very fast and detect if there's a failure very fast and kill the pod, bring up a new pod. And sometimes these data workloads need to do things like checkmark or checkpoint where they are in data processing. They have these new concerns with stateful applications. Sometimes the scalers are too fast. There's different network configurations. Do models have gravity? Does data have gravity? Even people are finding in some cases that data is cheaper to move closer to the compute. And so, there is all fluctuation of these patterns, and platform teams have to adjust to that. And so these are some of the challenges we'll see. Christina and Victor are going to go into real-world examples of how they implemented this. Just very quickly, there's different options for folks. By all means, you can do Spark, EMR in a serverless way using serverless paradigm. If you are doing things more native to AWS and you get some default services, lots of advantages. A lot of our customers choose Kubernetes to standardize. We have one of the best Kubernetes services out there in EKS, and there's different ways to run Spark. Because of the ecosystem you have, you can use an operator, run Spark on your own. We, of course, have Amazon EMR that runs on EKS as well as an option to give you kind of the best of both worlds between management and flexibility and the best open source frameworks. So Kubernetes and data, right? When we talk about it, there's lots of different patterns. Early on started with storage and custom resource definitions, moved on to event-based applications with Kafka that gives you event streaming, messaging. Then we get to Spark with the architecture moving from disk-type Hadoop workloads to in-memory intensive parallel processing. Then we get into Apache Flink, which is like I need both real-time data and I need batch data, and I need to do processing across them both. We get into I need GPUs and other types of specialized hardware to run intensive maybe training models, et cetera, and specialized schedulers and supporting things like notebook as a service. So we have an evolution of Kubernetes for data. We have a project. You take a picture really quickly, data on EKS. If you can come to us afterwards, lots of different blueprints and best practices to help you provision different patterns like running Spark on EKS or running Flink on EKS or running Kafka on EKS. So we have different types of scripts that kind of help you get started. And on the last point, when we talk about data, there's really a life cycle. So we talked about the support that a data platform needs to have. So for example, how does the data get into your environment, into your system, ingest, and you need to support different types of tools. Kafka-based things. You can do managed services like Amazon MSK or run Kafka on Kubernetes. We have native options like Kinesis, et cetera. And then we have workflow tools that kind of help stage the data, whether it be things like step functions or Airflow or Argo workflows, different batch schedulers to have some instances come up, and more stateful patterns. And we already talked about data processing. Then we get into the data processing tier, and we get into things like batch scheduling, doing kind of all the processing you need overnight. And then you want to get your data out and consume it. You might do some transformations, might do some SQL against it, different catalog the data and make the data available as an API. So this is the life cycle of the data. And so with that, we're going to go deeper. I'm going to hand it to Christina. Christina, I gave you a minute back.
Thank you, Roland. Hi, everyone. Next, I'm going to cover 3 things that you can do so you can optimize your analytics platform on Kubernetes for growth. So you're set to bring in analytics workloads fast into AWS, as well as grow into different regions. My name is Christina Antonov. I am a solutions architect, and I help you, our customers, building analytics platforms on Kubernetes. And as Roland mentioned, one reason that you might be here in this room is that you're already running your business applications on Kubernetes. You feel comfortable using it, scaling it, and now the analytics workloads are coming in. So when we engage with customers like that, this is where we usually find them, having 2 separate teams, building 2 separate platforms centered around the same compute. And the reason for that is not that much the compute itself, as it is the traffic pattern of the workload that lands on that compute. See, for business application, the traffic pattern is much like the weather in California. For the most part, you get highs of 80s, lows of 60s, and with minor exceptions, it is very predictable. The traffic pattern for the analytics workloads, well, that's more like the weather in the Caribbean during the hurricane season. And when that flood of jobs arrives at your clusters, that data platform team's responsibility is to make sure that these clusters can scale in a very short period of time so they can ingest the jobs, are optimized so they can process the jobs fast, and can do all that cost efficiently. So next, let's go over some best practices of what you can do to optimize these clusters. And when I mention best practices, because I'm assuming you're already running your business applications on Kubernetes, I'll just go over the delta of best practices between your business platform and your data platform. We're going to build a cluster with best practices from the ground up. We're going to split the build in 3 logical layers, where layer 1 will be building a vanilla yet production-ready cluster optimized for analytics. Layer 2 will be installing various open source tools to make that cluster purpose-built cluster. And layer 3 will be onboarding your tenants on that cluster. And actually, before you even create the cluster, you have to set up the networking to make sure the network will scale and you have enough IPs, because you might have heard that with IPv4, IP exhaustion is a thing. And your natural inclination might be to use an overlay network. But overlay network will inevitably add a little bit of latency, which is counterproductive to what we want to achieve here. So instead of an overlay network, what you can do is use this special range of non-routable IPs and add, in this case, in this example, 2 CIDR blocks that will give you 130 IPs to use for the nodes and the pods. Here is where I usually get the question, but how about IPv6? And yes, IPv6 will make all of our exhaustion problems go away eventually. Kubernetes supports IPv6 since 2 years ago. Spark supports IPv6 since last year, version 3.4 or later. But chances are something somewhere along your stack or that your cluster talks to might not yet be supporting IPv6. So it's definitely an option, but if you choose to use it, please test it thoroughly. Either way you go about here, I'll consider you have enough IPs, and then we can proceed with creating the cluster and start to put the add-ons onto the cluster. The first add-on that goes in is the VPC CNI. And the VPC CNI comes with this default setting, warm ENI target 1. What does that even mean? Well, what it means is that when instances come up, they have an ENI, and that ENI holds a set of pre-warmed IPs. One of those IPs goes to the worker node, and then as pod comes up, they get assigned IPs from those pre-warmed IPs. Now, if that instance were to be a C5 2 extra large, that ENI will hold 15 IPs. But for analytics, we tend to use much larger instances, such as C5 18 extra large, and that instance comes with 2 ENIs, and they hold 50 IPs each. That is 100 IPs. Well, for analytics, our pods tend to be larger as well, which means you're not going to schedule nearly as 100 pods on this instance, and all these IPs, most of them will go wasted. And that pool of 130 we just set, that might not be enough. So what you can do here is set max CNI to 1 for the VPC CNI, and then the second option here, max pods 30, that is setting on the kubelet. You can set it to a static number like 30. Or you can check our data on EKS blueprints. We have different patterns where we set that option automatically based on how large the instance is for different flavors of Linux. Last thing for the VPC CNI tends to be very chatty, and who it likes to talk to, it's its best friend, the EC2 API. See, for each and every of those IPs, usually the VPC CNI makes a call to the EC2 API. And if you're trying to bring up one instance, that's not a problem. But if you're trying to bring 100 instances at a time, well, guess what? You're going to throttle the API. So what you can do here is set up this enable prefix delegation. What enable prefix delegation does, it packages 16 of those IPs in one query, and it queries the EC2 API. That will reduce the queries to the EC2 API fold 16. All right, VPC CNI set. Next, I have a riddle for you. Do you know why CoreDNS gets invited to all the parties? Because it resolves everything. Well, most of the time. For analytics, usually, CoreDNS has to scale up proactively as a lot of instances are coming up. And in the past, you had to use this open source project called Cluster Proportional Autoscaler in order to scale CoreDNS. And I have good news for you. In May, we announced managed scaling for CoreDNS. That means if you are on version 125 of EKS and CoreDNS 1.9, and you have upgraded one time to those versions or later since May, this feature is already available for you, and all you have to do is just enable it, and then CoreDNS will proactively scale for you. You should also install open source project called Node Local DNS. Node Local DNS is a daemon set that you install. It runs on every single node, and it caches the queries, so it alleviates the queries that go to CoreDNS. And one last thing here, let's talk a little bit about how CoreDNS resolves external domains. If we give it a domain like s3.amazonaws.com, it will go into its configuration, and there's this setting called n.5. It's going to see n.5, and what that means is CoreDNS will look at that domain and say, oh, this domain has 2 dots, and 2 is less than 5, so this must be internal to my cluster domain. So what I'm going to do is I'm going to go here and append every single option in this search line, and that will result of in 5 unnecessary queries before I go externally and check where that domain is. One thing you can do here is, first and foremost, please do not change the n-dots of 5 to core DNS, but you can set n-dots to 2 on the pods only. What that will do is it's going to take a look at the domain. It's going to say, oh, it has 2 dots, and I'm going to resolve it right away. It's going to result in 1 query. And that will alleviate the pressure on the core DNS pods, and that's how core DNS can keep its party celebrity status. Next, for your business applications, we're going to scale some compute here. So for business applications, you tend to use this open source project, or a lot of our customers tend to use this open source project called Cluster Autoscaler. Cluster Autoscaler scales up the instances based on CPU and memory. And then what it does, how it scales instances, it usually takes on average like between 2 and 3 minutes to bring an instance up. We see data platform teams are the first to switch to another open source project called Carpenter. Carpenter came out from AWS. We open sourced it, and we donated it to SIG Autoscaling last year. And this year, we graduated it to GA, so now it's V1. It is stable. You can go ahead and use it. And the difference here with Carpenter is that one, Carpenter is fully aware of AWS pricing. So not only it's going to pick an instance that is going to fit the pod's memory and CPU speaking, but it's going to pick the most cost-efficient instance. Also, Carpenter is very quick on how it scales those instances up, much, much quicker. We usually see scaling the instance up in less than a minute. Before we dive into the Carpenter configuration, let's talk a little bit about how Spark jobs work. Usually when a data engineer submits a Spark job, a driver pod comes up, and that driver pod is responsible for managing the job. That driver pod is responsible for scheduling the executors, and if any of the executors get interrupted, the driver pod knows about it, it schedules another one, and it finishes the job. If the driver pod gets interrupted, the whole job has to start over. What that means for Carpenter is that we can install the driver pod to on-demand instances, and the executors are ideal for our deeply discounted spot capacity. As it comes to Carpenter, you can actually set one node pool and provide both capacity types in the node pool, and then use either annotations or labels or taints and toleration to land each workload respectively. Okay, great. Now we set the compute to scale. Next on the menu, we have storage. And when I say storage, I mean Spark Shuffle storage. See, we have these instance types with D in the name before the dot. What that D means is that that instance comes with a SSD drive built into the instance. That will be the fastest storage you get, hands down. So we recommend utilizing those instances and that storage. Now, some instances come with more than one SSD drives. And to take full advantage of the whole capacity, you should set these drives to RAID 0. Using Carpenter, it's as simple as instance stores policy RAID 0. I don't know if you've used this before, but this used to be a user data script that does some calculations. So this is awesome. Not only this is awesome, but you don't have to set the host path for the executors anymore. Executors will have direct access to that storage. Well, you still might want to limit how much of that storage they'll use in the Spark configuration, but that's about it. So for short-running jobs, this is perfect. But for long-running jobs, if that instance gets interrupted, well, the driver pods know about it, and it's going to bring other executors up. But now we lost the checkpoints. So these two executors have to start over. So if you have longer running jobs, maybe a better option would be to use EBS volumes. And in Spark configuration, we can do that. We can make the driver pod aware of these EBS volumes with this configuration. And that way, if the instance gets interrupted, another one comes up, the driver pod knows where the EBS volumes are, it attaches them to the new executors, and the new executors take off from where the interrupted ones left off because they have the checkpoint data in EBS. Last thing about storage here is that these two options are not mutually exclusive. You can provide both of them to your end users, and they can pick and choose which one to use depending on the job they're running. As I mentioned, Carpenter brings instances up very quick. The next thing that needs to happen is that that instance has to download the images and to run the pods. And good rule of thumb here is to have, from the moment I want an instance to the moment I have my pods up and running, is to have that process under a minute. So a few optimizations you can do here. First and foremost, get those images the closest to your instances as possible. If you're storing them in ECR, make sure they're in the region with cross-regional replication. If you're storing them in a different repo, we support pull-through cache for ECR, use pull-through cache, put them in the region. Set a VPC endpoint, so those images get downloaded through the network, and we don't have to go out and back in. And if that's not enough, and that might not be enough to get it under a minute, if your images are pretty large, meaning 5 to 10 gigs, what you can do is you can take large files out of your images, such as jar files and other libraries. You can store them in S3 Express Zone 1, and then have the images lean, and when they download, use S3 mount point to mount this S3 bucket as a drive to your executors. Okay, so now we get it under a minute, and last one in this first layer, please monitor. Set up your monitoring before you put this in production. I know most of you monitor Spark and the open source softwares that you're using. They come with metrics. I want you to monitor 3 additional things here. The first thing is, please monitor the Kubernetes control plane. We do expose the Kubernetes control metrics. Check out the EKS best practices guide, and make sure you monitor that. Make sure you monitor the AWS APIs. We do provide in CloudWatch metrics. And as I mentioned earlier, if you're using VPC CNI, you might throttle the EC2 API. Make sure you have access to those throttle metrics. CloudWatch is a data source to your Grafana or to your monitoring vendor, and watch those throttle metrics. Same thing for the EBS API. And last one, make sure you monitor the network. See, for example, Core DNS is using UDP protocol, which means if your contract table on the Linux, the connection tracking table, gets filled up, those Core DNS packages are going to get dropped. And you want to know about it from the Core DNS metrics. You need to monitor the network. Again, EKS best practices guide for monitoring the network. Check it out. And that concludes the first layer. So now we have a cluster that can scale, will be performant enough, and cost efficient. Next, we're going to add various open source software on this cluster to make it purpose-built cluster. The most common open source projects that we see customers use are Apache Flink and Apache Spark. Usually, the question is, do I put them together in the same cluster, or do I split them in their own cluster? And the answer to that is, well, it depends. If you have smaller clusters or clusters up to, let's say, 200-300 nodes, yeah, you can run them on the same cluster. But if your clusters start growing beyond that point, it will be good to start thinking about separating them. The rest of the talk will be focused mostly on Apache Spark here. For Apache Spark, we recommend, if you're running the open source version, to use the Spark operator. Earlier this year, the maintainers of data on EKS worked with the community and got the Spark operator donated to the Kubeflow community. And since then, we have seen tremendous bug fixes, active maintainers, so use Apache Spark. Another one here that is optional, like see the Kubernetes scheduler, you can schedule jobs on first in, first out basis. But if you're coming from like a Hadoop and Yarn world, you might want your priority queues or gang scheduling. And to use that, we recommend using this other open source project called Apache Unicorn that works really well with Spark. And last but not least, you will need some workflow engine for your jobs. Most common one we see is Apache Airflow. You can install it and self-manage it, or you can use our managed offerings. We also see a fair amount of Argo workflows, even lately step functions to do the workflow here. And that concludes the second layer. Next, let's talk a little bit about your tenant isolation strategy before we move on to onboarding your tenants. See, for some customers use one team per cluster, but we see the majority of the customers actually using multi-tenant cluster and using namespace as a service. And if you're using a namespace as a service, in that third layer, for your users, you have to create some construct like namespace, Spark API, even Jupyter Notebook, and a few other things in there. So let's take a look at this in a little bit of a different perspective. And the perspective is the following. Who creates the automation for each layer, and who consumes the automation for each layer? So for layer one, usually we see data platform teams. Their tool of choice is generally Terraform. So they will create the Terraform, and they will also consume that Terraform. Layer two is very similar. They will create the Terraform and some other tooling, but they will install this open source softwares and they'll manage them. Layer three, however, things look a little bit different. And what looks different is that the data engineers usually have to go through a ticketing system, or if they have access to use that Terraform platform, they're not very well versed, so they have to open the tickets for help. And one of the reasons for those tickets is actually these AWS resources, because the rest, we have some tooling. You can put them on the Helm chart. You can use like some other tooling. But if you have to create AWS roles, policies, S3 buckets, RDS instances, any resources in AWS with permissions, the data engineers have to open a ticket. A security has to approve this ticket. Somebody from the data platform team will pick it up, copy paste some Terraform, create this construct, and the compliance team has to audit it. Instead of using this process, you can optimize it by providing your users with a proper interface, which we think should be an API, and you can use the Kubernetes API to do so, and you can install this open source project on Kubernetes to extend its API in order to create IAM policies, S3 buckets, and so on. So ACK is an open source project that AWS open sourced a while back. Recently, this year, the EKS service team took ownership of all of the controllers for ACK, and currently we're at 50 GA controllers. That means we have coverage for 50 AWS services, and what GA means for you is that this is covered by your enterprise support. So using ACK, you can extend the Kubernetes API, and you can create APIs to onboard your tenants, and you can do the full namespace vending for them. If you're using one team per cluster, we see that those customers are trying to expand this to the whole 3 layers. But in general, this is where the majority of the customers are, and they're really happy with this. You know, in the beginning, when I started, and I said, here's where we find the customers, having two separate teams supporting two separate platforms centered around the same compute. And if you're an executive in the room, you are probably, well, is this a good thing? Is it a bad thing? What should I do about it? Should I put them together? What do I do? I'll tell you what to do. So you don't want to limit the organizational growth. You want to be able to, the number of platform teams you have is somewhat irrelevant. What you want to do is you want to standardize on tools and practices so you can foster that growth as it comes to your organization. A word on Terraform here. So when you start splitting your platform teams, let's say you end up with 10 platform teams and you standardize on Terraform, you're going to end up with 10 different code bases, guaranteed. So you want to standardize not only on the tool, but how the tool is used. Again, as I mentioned, we want to utilize the Kubernetes API as one of those toolings so we can provide APIs to our engineers. So the three things that you should do in order to set your analytics platform to scale are use the best practices that we just talked about so you can optimize those clusters for scalability, performance, and cost. Foster organizational growth, not by limiting the number of platform teams you have, but by standardizing on tools, best practices, and processes in your organization. And delight your end users with the interface that they can use to onboard onto the platform. Now, all these are great in theory, and it would be just theory if it wasn't for you, our customers, to put them in practice. So I'm delighted to say we have our customer here, AppsFlyer, and Victor will tell us how they not only put all of these into practice and a lot more, but they did it at scale.
Thank you. Thank you, Christina. Super excited to be here. Hello, everybody. Roland spoke about different options to run Spark workloads. What if I can tell you that only one decision can change your data organization? It can boost your performance, enrich your observability, save costs, and empower your developers. Sounds fictional, right? Well, I'm here today to tell you about the decision we made 1 year ago. My name is Victor. I'm working for AppsFlyer for the past 6 years. I'm leading the data platform group, responsible for the real-time and analytics data platforms. I have vast experience in AWS ecosystem and data processing. And one of the biggest benefits at AppsFlyer is that I can do it at scale. Did you know there are more than 7 billion smartphones? On average, there are more than 60 apps installed on each phone. If you will show me your phone and application, I will definitely recognize an app which has AppsFlyer SDK on it. AppsFlyer is helping app owners to optimize their advertising campaign and find the right audience for that app. We expose detailed analytics and handle massive amount of data each day to make it happen. Now, let's jump right into the analytics workloads and see how we run it at AppsFlyer. First, let's talk a bit about Spark. Spark is an open source analytic engine for large-scale data processing. You will find it almost in every organization that handles data at scale. Let's review some of its key characteristics. Spark is usually being used as batch processing for consuming and producing downstream data. Depending on the job, it will require different CPU, memory, and I/O performance. Processing time is very important, and the right compute and scaling strategies are a key factor. And Spark jobs are usually stateless in nature. However, if interrupted, they will require data reprocessing, which might affect your SLA. Now let's talk about the challenges at AppsFlyer with Spark jobs. We process more than 100 petabytes daily. We run thousands of very different jobs at any given moment. Our compute is widely distributed, from Intel to Graviton, CPU, memory, and storage optimized instances. Basically, you name it, we have it. We're very dynamic according to our data trends. We process millions of events per second, and our traffic can scale up and down very rapidly. And we must be very efficient with our scaling strategies. And finally, we're very strict with our SLA. As a data company, we must make sure we process our data in time. Otherwise, it will affect our business. So we decided that the best course of action in handling those challenges is moving our workloads from our original EC2 instances managed by configuration management and internal tools to EKS. Why EKS? Let's deep dive. There are several areas where EKS ecosystem excels when it comes to analytics processing. I'm going to mention 3 and show you the value. We're going to talk about Carpenter for scaling and compute optimizations, Observability, which can be enriched and give you valuable insights about your data, and enablement, how we empower our data engineers. Remember this slide? It perfectly shows the ingress, consume, and downstream. Let's focus on this area, the data lake. And let me show you, as an example, how our main data processing, compaction, runs on EKS. Compacted data is the result of merging small fragmented data files into larger, more organized files to optimize storage efficiency and performance. This is usually the first entry point for your data lake. We run it hourly, have around 150 jobs with different runtimes, and we process around 60 tera each iteration. I will start with Carpenter, which help us tackle our challenges and achieve our goals for compute, scaling, and cost performance. Take a look how our old EC2-based Spark cluster looked like before we switched to EKS and Carpenter. It was managed by configuration management tools and in-house. The yellow line represents utilization, and the purple represents the cluster size. You can see that the scaling mechanism is not effective. When our utilization drops, the node scale down cannot keep up. Carpenter solves it. It picks the right compute per our configuration and scales up and down efficiently according to our utilization. In each iteration, we scale up approximately to 60 nodes and back down when we end the processing. If we look at the utilization of the node, we will see that we peak at around 80%, which is our sweet spot, and stay stable in node capacity. We start to scale down only when utilization drops. Data processing is very expensive in terms of compute power. By doing this, we minimize our idle time and eliminate resource waste and unnecessary costs. In a 24-hour cycle, we're doing it more than 1,600 times, both for creation and termination. And remember, this is only our compaction workload. We have hundreds of other different processing workloads, so we can only imagine how our termination and creation node looks like on a daily basis. Let's look at the instance spread. Carpenter's strategy is picking the most stable and cost-effective node at any given moment. We use Graviton Gen 3 and fall back to Gen 2 when there is no capacity. We use spot instances only. And take a look at the bare metal node. Full control of the machine resources, direct hardware access, no hypervisor overhead. Very high performance. It is 15% of our node pool. When was the last time anyone manually picked bare metal nodes for stateless or dynamic applications like Spark? It also gives us the option to use new gen instances, and we can provision them as soon as they get out. We also distribute a node across multiple availability zones. Carpenters make sure that we provision on the most cost-effective zone. Zone A was the winner that day. It had 20% more nodes compared to Zone B. We also ensure that our job pods run within the same availability zone, eliminating cross-AZ data transfer and its associated costs. But not all was well that day. We had many spot interruptions during those 24 hours. In some cases, dozens in 1 hour, which should be devastating to our SLA, right? However, due to the effective termination handling by Carpenter, we can hook spot termination signal to Spark, which gives us the option to migrate the intermediate stage of data within 2 minutes. This approach eliminates the need for reprocessing in the event of node failure. It makes spot termination nearly seamless to our workloads, keeping us well within our SLA, and the longest job during those 24 hours was only 33 minutes. I've shown you some nice results. Now let's see how you can achieve near the same performance with a few simple configuration changes. For scaling, we use Amazon Linux 2024, optimized for fast boot time and kernel performance. This allows us to provision nodes in under 10 seconds. For decommissioning, we adjust our node distribution budget according to our processing trends. We set times when we can decommission more aggressively to reduce the idle time, and less aggressive when we are usually at peak utilization to maintain high performance. This configuration is being used for Spark to be aware of node termination and enable Spark shuffling. And to ensure we can migrate within 2 minutes, we utilize local storage for optimal performance. To enhance resiliency and cost efficiency, we configure each Spark job to run within the same availability zone. Again, eliminating cross-AZ traffic and its associated costs. And this section defines the use of Graviton instances with local storage for optimal performance. Now, I must say that we try placing specific nodes, but no matter how many variations we try, Carpenter automatic selection consistently outperform in terms of cost efficiency. We're done with tuning. Now, let's talk about what we can do with observability. We saw how Carpenter helps us manage and scale our compute. Now let's see how combining the metrics from Carpenter, Kubernetes, and Spark helps us get some valuable insights from our platform. How many of you know what is the percentage of each data processing flow? In compaction, we know exactly what is the ratio of every processing and when it starts and ends in each processing cycle. Here you can see that clicks takes around 28% of the workload and start at the mid of each cycle. This allows us to see the distribution and weight of each dataset at any given moment. Moreover, we can see daily, weekly, and monthly trends and understand our system and business implications. Look at this metric. we can see that click processing was reduced by 8% compared to last week. And a different data set was increased by 35, which might be a bit concerning, right? By examining our Datadog query, we can see that this information can be easily obtained by combining metrics from Kubernetes and Spark. But what happens when we add Carpenter metrics for price estimation? Carpenter sends us cost per instance and AZ, and by adding to Spark and Kubernetes, we can calculate how much each data processing costs. So we get the price for processing our data per minute in near real time. This is huge, both for engineering and business purposes. You can tell how your code deployment affects the cost and take decisions according to the trends. You can even set a better pricing for the service you provide for your customers. You can even take it one step further by integrating this into your data lineage, allowing you to determine the total cost of your entire data processing pipeline. You can decide what can be optimized and what is redundant. Combining your observability metrics gives you a comprehensive view of your data flows and allows you to take data-driven decisions about your data. Well, all those metrics and performance I showed you worth nothing if only platform engineers know how to use it and tune it. And I showed you only a few of the options. We encourage and give our data engineers full autonomy and control over their applications and platforms. We, of course, provide best practice, defaults, and policy, but they can change and override depending on their needs. Everything is being done through our source code. We created a detailed Git structure, which defines the action of the repo, deployment units, both for infrastructure, application, and third-party integrations, and environments, which segregates between development, staging, and production. Each has its own GitOps flow. This approach allows us to manage the infrastructure, Kubernetes, and application components from a single interface, enabling automated workflows and validation for executions and deployment. It protects us from configuration drift, ensures we maintain the current state, and allows us to spin up and modify application and infrastructure within minutes. And finally, this removes the dependencies of our platform engineers. It raises the velocity and autonomy of the data engineers and contributes to the knowledge of both. So at the beginning, I presented that one decision changed our data organization. As you noticed, this decision was moving Spark workloads from EC2 to EKS. Now let me show you the value. This is a young version of me. Compared to our old EC2 Intel-based Spark clusters, by using EKS, Carpenter, and Graviton, we reduced our cost by 60%. We improved our SLA by 35% and significantly enriched our observability. And the cherry on top, we reduced the operational overhead of our platform engineers and raised their overall happiness along the way. Thank you.
All right. So, excellent presentation. Thank you both. If you take anything away, right, optimize and monitor EKS for analytics and best practices. Align tools and practices to foster organizational growth. So we saw the layers that Christina talked about, so you can be happy like Victor. And provide APIs. Remember, developers, data engineers, data scientists are your customers of the platform. If they can't build, if you can't provide them APIs, all you're going to have is a platform not being used. So enable APIs to empower data engineers to work independently, autonomy, while you're still providing the automations for control. We have a happy union together. So thank you everyone for joining. Don't forget, for session resources like data on EKS, you can click and scan the QR code there. Thank you for coming, everyone, and enjoy the rest of the conference.